here. So there's a whole open questions, so there can be other algorithms naturally where you might want to might have some natural parameters. So I guess one of the critical things is to identify which are the most impactful hyperparameters to tune, and then you can try to apply these tools to understand how complex the behavior is as you vary those hyperparameters, and that's captured by some of the tools that we introduce in this line of work. So those are extensions to other problems, and we have reduced this solution of a new problem by developing these sort of general tools like the FAFI framework. At the same time, there are questions which are interesting even for the existing applications, things like computational efficiency, especially in high dimensions. There is much less work on this and much more interesting questions about how to tune these hyperparameters in a computationally efficient way. Then maybe even give lower bounds, complexity theoretic lower bounds, both on the computational efficiency and the sample efficiency. So we have some examples of these results, but only for very specific problems. Not like we had this wide, I showed you a few slides ago, like a whole bunch of different problems for which we know sample complexity guarantees, but those are upper bounds. So lower bounds and computational efficiency are not known except for a small number of cases. Right. So let me move on to a concrete example, decision trees. So that's the context for decision tree especially is important today because you want your machine learning algorithms to be interpretable. They're black boxes, and decision trees are kind of treated as this gold standard for explainable machine learning, right? So you have your input, you have your output, your machine learning model does something, but we don't really know what it's doing, and should we trust it? Okay, if you're using it for making decisions about people's lives, like or maybe using it for hiring or deciding who to give out a loan to, they can have serious consequences if the hidden algorithm has biases from its training set. So you really want, if you're deploying these algorithms, to be more transparent, to reveal what factors were involved in its decision making. And decision trees do that naturally. Like the whole structure of decision tree is completely transparent. It tells you exactly the sort of features that are involved. So just to remind you, you can use decision trees for classification. Each internal node of your tree is like a splitting rule. It tells you, if this feature is this categorical feature takes this value, or this real valued feature is in this range, then go left or go right. So it tells you how to follow the tree to make decisions on any new example. And each leaf